Okay. Hopefully you can hear me. Can you hear me, guys? Can you hear me? Okay. Yes, I've got some response. People can hear me. That is good. Okay, so let's. This is the last part of the session. We are having these 40 minutes. Will take us up to 8 when the lecture is supposed to end. Okay. So we had now got the expression for N naught. That is the first Fourier coefficient. Then for the other coefficient, that is AN and BN, we'll get equation 3.41. And what we are going to do here is we will multiply all through the entire 3.41 by cos M pi x over L. And once we will do that, we will have a cos, and then we'll have a cos sine. So that's what we are doing. After getting N naught, we are saying multiplying equation 3.4.1 by cos and then integrating. So if you do that, you have this fx cos. Be mindful of the 3.41. We are simply multiplying each and every term here with the cos m pi x over L. The pi, definitely when we talk of m pi, m keeps changing, and that caters for the periodicity exhibited by these trigonometrical functions or series, okay? So here, when we take cos, you multiply here, and then you have it equal to this. So you can see there is a cos there, and that is the N naught over 2. Then there is a cos here, and there is a cos there. Now we bring back our condition. M not equal to N, that is 0. These ones, please, what I am putting down here, but by orthogonality, this part here, we have already looked at it. We are simply recalling it. This one we have up there, guys. When we say by orthogonality, this one we already have. We have already discussed this, this part here. By orthogonality, this one we said it is 0. Remember, there is like a 1 there. You also have sine alone, it is 0. Cos, this is where the difference is now. It will be 0 for m equal to n, and it is L for m equal to n. And of course, when you have this m equal to n, this one will give you, when we say m not equal to n, because you'll have, let's first go. Yeah, we are, okay, we need to come here first, clear this one. So what we are talking about is this part here. Yes, here, we have this part. Remember, we said cos and cos, this one will be 0 if m is not equal to n, but cos for m equal to n, this one will simply give you L. And that is this part here, because if you have cos and the m is equal to n, then you get the square. I think this one must come out very clearly here, because some of you may be wondering, we don't see the L. Here, if it is m not equal to n, then it will remain cos m, cos n. But for m equal to n, which is this part here now, if m is equal to n, then it means this is the same as that, and then you bring in the square. And if you integrate over that same interval, that is the cos squared mx, meaning n is m, that gives you L here. So the others are zeros. And this now can help us to simplify what we have the other side. All right. Okay. So with that in mind, we can come back here. Okay, okay. I was going through the charts, seeing if there were questions there, but most of the time I find there are nonsense. That's why sometimes I even forget to look there, and sometimes when the session ends, I lose all of the charts. So I hope those who usually have meaningful charts, they are not bundled in people's private talk, and then you miss out on getting a response from me with respect to what you have asked. So for those who always put their meaningful questions that I should answer, and somehow they are lost in what the America would call non-value adding statements, then he doesn't really call them non-value. For him, he would use the word S, but because I am in the month of the Rosary, I don't want to mention the S in the full. So most people there, what they write is full of the S word for the American. But pardon me, I will not mention it. So unfortunately now some of your serious colleagues have serious questions, and then I miss out on seeing those questions, because when you go there, you find funny statements. Okay, so let's finish up with the second part now, the AN now. The AN, which is one of the Fourier coefficients. So taking this into consideration, if you take now this into consideration, this part here, what would this amount to? If this is the case, we are now saying cos sine, this would be 0. So this whole thing here goes to 0. Okay, but remember m is n. So if m is n, here you're going to get cos squared, implying that this integral here, the whole of this integral here will give us L, just the integral, meaning we will get a n L. And once we get that on the right hand side, we make this Fourier coefficient and the subject. And once you make it the subject, because it will have to cross to the other side, that's when you'll get, let me just clear this one. That's when you'll end up with this statement here. The 1 over L, then the integral of course, when you simplify, it is going to come to this one here. It is, where are we getting the L? Okay, A and L is established here, and it is this that we are equating to. We are equating to this one here. So remember, it is this equal. So in getting this equal, it means that this one here, after the simplification, this is A N L. Now we are making L the subject, rather N the subject, A N the subject, meaning your A N alone will be 1 over L integral of this thing here. So this will be the expression for the second Fourier coefficient. And then we repeat this process. Now what we are going to do is to repeat this process, but this time, in repeating this process, what are we going to do? We are we are going to multiply by now sign. So when you multiply now, our equation is 3 point, this is 3.4.1. We are now going to multiply it with the sign all through. We bring in those same definitions of orthogonality. That is this part. Then we'll get to the BN. That is this section here. Multiplying equation 3.4.1 by sine m pi x over L. If you do that, you bear in mind, these are what we have been discussing here. By these, I'm referring to that part there. Okay. So if we multiply all through by sine, we get this. So what we are going to end up with is simply a BNL. This one will be equal to a BNL. Why BNL? Remember, m is equal to n. Here you have sine squared. Sine squared, it means this integral here, the whole of this integral here is going to give us L. Then remember, this is a cosine. M is not equal to n. Here, this part here, this whole integral here will go to a 0. So once you have BN will now be 1 over L, then that integral, which is what we have here. I must be very clear here that all of these derivations, you could be assessed on them. You know the different modes of assessment, so you can be asked to go and prove that indeed the Fourier coefficient Bn is this one here. Right. Okay. And from that, we can now have some examples. We can do some examples and we illustrate. So let's go through this example. The remaining time will be enough for us to go through this example here. So we are going to go through this together. There is nothing big here, really. The key thing here is simple. Why simple? What we are saying basically here is the only basic thing here we are talking of is techniques of integration when it comes to the actual applications. So we can rush through this example, and what is the key is basically how to integrate. So all of that we have discussed up here has been summarized here, guys. So from our definition of trigonometrical series, that is the definition. Then we applied the concept of orthogonality, and we established our Fourier coefficients as it is. So in expanding and getting, if you are given a function fx, so the only thing missing in here to get these coefficients is knowing the type of function you have, which is fx. After knowing the fx you have, then we also need the interval, the minus L and L. Once you have the fx, of course, this is highly likely that it will demand that you use integration by parts, even this one here, depending on the nature of fx. This one is certainly, probably, unless if you have a function which is a product, but otherwise this one could be direct integral. But in AN, Fourier coefficient AN and BN, those ones usually demand for integration by parts. I'm not going to take time on these different integral forms because you are already experts in that. Okay, so I'm remaining with what's the time? I'm remaining with something like 23 minutes. Yes, 23, given that I'm not going to dwell on the techniques of integration, the time will be enough for me. Okay, so there is an example here. The periodicity, this one I've already discussed that. We have talked about these ones, those are Fourier coefficients. Okay, so there is a simple question here, very simple question. What we have now here is simply some function fx, which is piecewise. And here now, what we had as minus L to L. In this case, it is given as minus pi, guys, and this is to pi. So now we know the L is given as that. Our function fx is piecewise. From minus pi to 0, it is 0. So that part of the integral can easily disappear. So we remain with this part here, which is positive. That is pi minus x to x, rather pi minus x, which is 0 to pi. So that is basically it. We already know that L, we just have to substitute directly. So remember, we already have the notation. So where there is L, you substitute pi. So our N naught, by definition, it is given by this. That is what we have. So we know our fx, but remember the fx is 0. So when you expand this, given that the function is piecewise, we can take out we are factoring the 1 over pi. So that is the 1 over pi into a box bracket. Negative pi to 0, that is 0. Then we take this other one, 0 to pi over pi minus x. Normal integration. You realize that your N naught is this one here. You have got the first Fourier coefficient. That is it. There is nothing big there. So the next part, that is integration by parts. And sincerely, we have been integrating by parts even in Laplace. So you just have to think of the U and you think of the V. And then you do the needful. Huh? I wish people in the chat could just tell me, omit that one and I omit and we do other things. Guys in the chat room, can we please omit this one? Because everything here is obvious. Can I hear a yes? Oh, people have already said yes. This is good. So we can omit this one, I think, because everything is really direct. Yes, Vatesaki is saying yes, we omit. Nazua is saying yes, we omit. There are very many yeses. The good thing they are no-nos. Since we don't have any no, you see I am boring you with the obvious now. Everything is direct. What I'm seeing in the chat is only yes, 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 yes. This is good. This is very good. Even Jojo has said yes. This is perfect. So since we have got only yeses, I think I have not seen any no there, implying oh, there is one no I have seen here from Majezi. Okay, let me just highlight and we continue. So in this case now, it is integration by parts. Let's rush through. We are remaining with 19 minutes. Trust me, they are enough. Even if this session runs out now, Mia and I have already handled this integration by parts. It is your work, so I will just leave it at that. But because we have overly discussed this. So let's look at the AN. The AN is quite direct. That is this one here. That is the part in blue. So what do we need here, sincerely? This is just integration by parts. So when you split up this, remember our function is piecewise. You are moving from minus pi to pi fx, but remember we have the 0 part, which is this one, and then we have that one. Now remember we had cos n pi x over L. I think you remember that. But now it turns out that our L is pi. This L here in the denominator. It is pi. So when you substitute L with pi, this pi will cancel with that pi. And once the pi cancels with the pi, you remain with the cos nx. That's how you end up with this. That is direct. Okay, but now you have to be mindful of this cos nx, because anyway, we'll look at that after substituting. Okay, so once you have this integral, this is where now the real worker is. And once I illustrate it for this one, I don't have to illustrate it for Bn because it will be the obvious thing. By obvious, I imply it will be a replica of what we'll have done under An. So now here, the real secret is on integrating this part here in red. Is that okay? This is where the actual worker is. So how do you integrate? Actually, even I'm circling it off poorly because the bracket should not be part. It is this integral now that we have to look at. This right here. That's what we have to look at. So what is interesting about this is we are dealing with two terms, okay? So the first thing is what do we deal with here? Remember the integration of this is the integration by parts. We know that the integral of what? This is the integral of u dv. Is that okay? This is equal to you have u v minus the integral of v du. This is u here. Is that okay? I think we are together there. This is v du. This is u dv. So what is key is simply picking the u and the dv. So from here, which one should we differentiate? Which one should we integrate? Really make sure every time you try to differentiate, don't differentiate and you realize that this thing is you are increasing x. There you will be complicating things. So since x can be reduced to a 1 when you differentiate, then common sense suggests that you let the pi minus x be a u. So if you let u be your pi minus x, then what does that imply? It means that the du is what? Your du will be, you are differentiating this with respect to x, your du will be a minus 1. I think we are together there. Then if we let dv, then we can let dv be equal to cos nx. I think we are together there. Now we need to integrate this one to find v. What is v? I think you all know that this is, what is this? This is a sine. So this is a cos. So if we had a sine, differentiating the sine would give us a cos, meaning integrating the cos would give us a sine. I think I am right there. If you differentiate sine, you get cos. You integrate cos, you get a sine. So our v is simply n, 1 over n sine nx. So this is sine nx, and this whole thing is over n. Remember, we have some n. When you differentiate sine nx, it will give you n cos nx, and integrating the cos would give you 1 over n sin nx. I think we have everything we need. So now let us substitute into this one. Guys, I'm hoping we are together. So if we substitute, I was trying to see what was in the chat. Someone is saying he's not seeing 1 over pi. What do you mean you don't see 1 over pi? I don't understand this one here. This is Eguero Solomon. Okay, Wilson, it is 1 over L. Okay, I don't really get what these people are saying. But anyway, the 1 over pi is already out here. I don't know what, I have my 1 over pi, which is here with the box bracket. But hopefully you'll follow me up to the end. I'm remaining with the 12 minutes. So if there are other questions, I'll find them in the chat. Okay. We are doing parts. I have already got the u. Our u is pi minus x, guys. The u here, remember what I have referred to there. The dv is cos nx, which is this one here. So what I have basically done is that I have considered this one here to be u, and I have considered the one in blue to be dv. I think we are together. So that is the substitution into this. Now, we are looking for u and v. So the u, in getting u, we have it as this one here. Our dv is, we have got u, the u is pi minus x. And then the v is sin n x over n. So if you do that, from this, you can see this is the part here. If you look at this inner part right here, this is this term here. I hope we are together. That is the term in blue. If I substitute for u and v, the u is the pi minus x, which is this numerator. Then the dv is what I have integrated here. This is my dv, rather the v. The v is the sin nx over n, which is the n in the denominator, then sin nx. Okay, so it is minus integral of v. So that is the minus integral. Now that is the second part here. I am highlighting in the red. Minus is there. So let's look at this one here. So what is red? We are saying it is a v, but what is v? This is a v. Is it v du? I think I'm confusing something here. This is v du. Hey, how come I'm getting something else? So we have 1 over n squared. Am I confusing myself here? Probably yes, probably not. Why are you getting 0 for the integral from this Madam Nasasera? Someone is asking, why am I getting 0 from minus pi to 0? Nasasera, look at the function, please. From negative pi to 0, it is already 0. Some of you, I think you've just joined the session. This one is asking, why are we getting 0? It is because this one here is 0. We are getting 0 because of that 0 there. Okay, let me first finish up with what I am doing here. Otherwise, these ones are going to confused me a little bit. Okay, so what I was trying to check out here is the second term. The first term I have got it. That is this one here. This one comes out nicely. I'm getting the confusion here. Okay. I have seen where the confusion is coming from. This thing is already integrated. Sorry. So we have to I call came through and my network was cut off. Sorry about that. Sorry about that. Let's finish this. What we are doing, I'll just continue with the, I think the recording is still in session. Okay, that's fine. Okay, guys, let's finish up. Okay, I've lost everything, but I can easily pick up from where we had stopped. So I was trying to explain this term here. This is I was trying to explain this term here. Where did this term come from? That's what I was trying to explain. Remember the last part we had a minus integral of v du. We already had the uv. The uv is already catered for here. That one we had. So remember we had the v du. But now what was our v? Our v here, the v was 1 over n sine nx. That was our v. And the du was minus 1. I think you guys, you still remember we had the du, which was a minus 1 when we differentiated this part here. So this is a minus 1 dot. The du is minus 1, the v is that. Remember you are integrating, but this minus goes with that minus. This minus should go with that minus. So first of all, to make this one a positive here. But now you have 1 over n. Then we have to integrate the sign here. So when you integrate sign, remember when you have cos, we are integrating this. So if you had a cos and you differentiated a cos would have given you, you have cos nx. This would have given you, differentiating that would have given you a minus 1 over n sine nx. I hope we are together. Meaning integrating sine nx, the integral of sine nx. This would give us a minus 1 over n, then cos nx. I hope we are together, guys. But remember, this minus goes with this minus 1, which gives us a minus. So you have a minus 1 over n cos, but there is also a minus 1 over n, which is a positive 1 over n squared. When you substitute, you'll get back here 1 over n squared cos nx. That is very true there. Okay, then what you do is you throw in the limits. So when you throw in the limits, what do you get? Throwing in the limits here, when you throw in the limits, what are we supposed to get? Remember the limits, you move from pi. So when you throw here pi minus pi, this will be 0. The upper limit will give you 0 here. Why is 0? Because pi minus pi is 0. So this term will be 0. Then when you throw a pi here, now that is the interesting part. Now cos, this will be cos n pi. And this cos n pi is the same as minus 1 to the n. Now you just have to keep iterating this, because this one can also be simplified to odd and even. If n is odd, what will happen? If n is even, what will happen? So for each value of n you throw here, you realize that if n is 0, you are going to get a 1. If n is 2, you'll get a 1. If n is 4, you will get a 1 here. So it implies that if n is even, you get 1. But if n is odd, you will always get this, because you realize that if this is a 3 here, then this will be a negative 1. If this is 5, that will be a negative. If this is 6, but then the question is, if cos is 0 here, cos 0 implies what? This being 0, that will give you cos 0. And if you deal with the n cos, so let's look at 1, you have cos 0. And then you have cos pi. Pi, now that is for n is equal to 1. If you deal with that kind of integration, remember I've already told you, when you look at cos and sine, you always oscillate between minus 1, 0, and then 1. That is always the case, whether you like it or not. And due to that simple fact, then it would imply that you will either get always a 0, or you will always get a 1, or you can oscillate between 0, 1, and minus 1. So we also know that every time you compute cos of 0, you'll always get 1. So anything that will give you a 0, so cos 0, but you get cos 0 when you've substituted an odd what? When you've substituted if n is 0, this will be a 1. Then what about 2? 2 will give you, that will be 360. So cos of pi, that is cos of 180. And we all know that cos of 180, this one here, this one will give you a negative 1. I think we are together. So why are we talking of minus 1 to the n? Because the answers will always oscillate in either positive 1 or a negative 1. So for any odd, you will always get, negative 1. Guys, I'm going to request that you log back in for just some 10 minutes if this session runs out, to finish this example, please. As soon as this, I think we'll even need 5 minutes. As soon as this session runs out, please log back in and we finalize this example so that we